So vanakkam. So we will continue today lectures on engineering seismology. So last class we discussed about the wave character and application of the wave character on the different part. So we have seen that if you know the wave character very well, so you can able to know what type of wave you receive and you are in the P wave shadow zone or S wave shadow zone. So you are your seismic station, and when these waves are coming, so which type of wave you can expect with reference to the origin of the wave to the your building, that we are understand. And also we have seen that there is a deep geophysical investigation has been carried out. People try to map a stiffness and then the density variation using this wave understanding. Okay, so that is a so today class. So as we, since we discussed about the wave, today class we are going to see how these waves can be recorded. Okay, so that what equipment is used, how this equipment was development. So the earthquake recording instrument, the concept of seismogram and build your own seismogram is going to covered in the today class. So the instrument which records the seismic signal, okay, is called as a seismoscope or seismometer, which we have seen already. So this earthquake recording is not the new thing. Okay, so this is exist since ancient time. Okay, so particularly it was exist since Asia in 1932 AD, dated 1932 AD, the seismoscope has been found. So if you remember, when we talk about the earthquake, I also shown a earthquake god. One we have shown a Bhuma Devi, another one we have shown one Chinese symbol basically. Okay, so next to that Chinese symbol there was a person who was holding a small kind of jar and standing, that is a Cheng Hen. So basically the seismic seismoscope, okay, seismoscope has been invented by the Cheng Hen in 132 AD. Okay, that is the time where the seismic instrument has been exist. So how this instrument was? This was a like a very big jar, okay, which has about 6 feet diameter. Okay, you can see 6 feet diameter jar, which has basically 8 dragon. You can see the 8 dragon around this. So you can see the dragon. This is the one dragon, 2 dragon. This 8 dragon oriented on the 8 direction of the earth. As you know that we know the 3 major 4 directions, no, north, south, okay, so east, west. So if again if we link the northeast, southeast and so southwest and northwest, you will get a another 4 direction. So this 8 direction there is a dragon. So this is the dragon. You can see very closely this dragon is holding something. So what it is holding? Basically it is holding a ball. You can see this is the ball. Okay, so then there is a toad. Okay, so down below the 8 dragon there was a 8 toad. This toad was opening his mouth. So the dragon mouth there is a ball and then toad was empty mouth, it's opening. So whenever there is a earthquake occurring, okay, then the dragon will drop a ball, the toad will catch that ball. Okay, so this is what happened. So this seismoscope has been used to identify a earthquake like this. So particularly this is very interesting. The direction of the earthquake is very well known. Okay, so that is what this seismoscope provided. So how far you can record? Basically it can detect 400-mile distance earthquake which was not felt at local by the many people. So it can detect any earthquake occurring from 0 to 400 miles, that is close to 600 kilometer. That was the highest very sensitive equipment one can see in 132 AD. Okay, so that means 400 miles, beyond that something happens, this instrument capable of recording or notifying that earthquake by dropping a ball. Okay, so the inside seismoscope, Chinese seismoscope is not well understood up to last year. Okay, there are many people tried which was not possible to understand, but last year there was a article published, video and article published after a 5-year study of the Chinese seismoscope, how it is working. Okay, So, but when I started this course, actually this not well understood. So, that the same thing was I also continue. Now, it is very clearly written how the Chinese seismoscope is working. So, if you want, you can go through that. But when the seismologists want to develop a seismometer in 19th century and 20th century, those time the Chinese scope is not well understood. They do not know how it works, but it is able to detect a earthquake direction. So, I may be suspicious that these people predominantly they might have used this Chinese scope basically to know the direction of the earthquake, particularly in Japan kind of countries where the earthquake occurring in the sea causes a tsunami where the people are suffered more. So, if you know the sea earthquakes on the tsunami seaside, the people might be escaped, because as you know that the tsunami wave reaches very long time. It takes a long time to reach a shore. So, if you know 600 means like 600 kilometers the tsunami waves, so earthquakes are happened, people had enough time like 1 hour, half an hour time they have, depends upon the origin and location, then they might have moved to escape or reduce the death. That is the reason they might have tried to know the earthquake direction rather a amplitude, because there that time maybe people and all will be living on the nature built house, okay, or the house which is built using the natural material which does not undergo a failure, okay, it does not undergo a much failure, even if it fails you will not hurt, okay, that kind of structure they might have been used. So, that is why they are very keen on identifying the location and direction of the earthquake. The Chinese scope was doing that very well, but seismologists want to develop, English people want to know that how these Chinese scopes are working, so that they can also develop a similar kind of equipment to record a earthquake which is happening since historic times. So, all assume that the use of some kind of pendulum as a primary sensing element, the motion of which would activate one of the dragon ball. This is the assumption, because they could not be able to cut and see the seismoscope. Even today the Chinese seismoscope is exists in China. So, whatever I was telling that last year there was a discussion and scientific article, people who are interested to know that you can go and study how this was built. They basically given a cross section, dimension, everything. So, to completely characterize the earth movement, the motion must be measured a 3 perpendicular direction. So, consequently the seismogram often employ 3 sensors recording each north, south and east, west and vertical direction. So, that is what you should do. So, basically the Chinese seismoscope is a translation is in original Chinese description. So, Cheng Heng seismoscope, English seismologist Millen, okay, implied that the pendulum was a suspended mass is a common pendulum which will help to get a activate a ball. So, later the seismologist Imamura thought an inverted pendulum was more probable way to activate a ball in the dragon mouth. Okay, the Hagiwara constructed a inverted pendulum seismoscope which behaved nearly as a Cheng Heng was reported to have behaved. The model designated by the Hagiwara, however, responded most frequently to transfer motion, indicated that the direction normal to the azimuth of between the observer and the epicenter. So, the Hagiwara basically tried to understand the seismoscope during 19th 20th century and tried to simulate, but he success some extent to activate a ball, but unfortunately the ball was dropping perpendicular direction of the wave. That means it is not dropping at a earthquake direction. So, they could not able to completely explain the concept behind the Chinese seismoscope. Okay. So, the later John Millen was the English seismologist and geologist who invented the first modern seismogram and promoted building seismological stations throughout the world, so that people can measure and understand earth interior and understand the earthquake and try to minimize damage due to the earthquake. Okay, so, the 1880 the James Albert Ewing and Thomas Gray and John Millen, the all British scientists working in Japan began to study earthquake, and John Millen was invented 1880 as the first seismogram in the world. So, now you can see that any earthquake which is recorded before 1880, you may not have the earthquake recording at all. So, this 1880 is how much? It is just about 120 years back, that is all, nothing more 120 years back. So there is no instrument that. So how it works basically seismoscope. So it is works with the pendulum. Okay, there is a pendulum. So it acts as basically stationary when earth is not moving. So when the earth is its own speed it moves, it is stationary. When there is a vibration take place, okay, it respond to the vibration and then try to give that graph. So the pendulum height and then mass in the pendulum plays a important role to level of vibration can be recorded. Okay. So this is how the seismogram works. Okay. So this is how the people started developing a seismogram at initially. So the simplest form basically a rotating drum connected with the housing of spring and dashboard system. So basically this is a spring and dashboard system. So arranged parallel housing connected to the ground. So this is actually mass which balancing. So when the earth is normal, so this basically this mass and spring and dashboard will be in balance position, it does not move at all. So this is the drum where that movement is monitored. So it will be like a straight line. So when there is a movement in the earth, basically it creates a relative movement. That movement is marked like this. You can see it is marked like this. Okay. So it is marked like this where you can get record of the earthquake. So this can be explained further. The seismogram can be designed to measure various ground motion characteristics. To understand how it can be done, it is necessary to consider a dynamic response of the simple seismogram. Okay. So such as one shown in the figure previously, based on the equilibrium of the equation, the force damped zone system. Okay, the equation of the motion can be given like this. Here the u is the seismogram trace displacement and the relative displacement with the seismogram and ground, and the ug is the ground displacement, m is the mass, c is the coefficient of the damping system, and k is representativeness. So if the ground displacement simple harmonic central frequency wg, the displacement response ratio, that is the ratio of the trace displacement amplitude to the ground displacement amplitude will be this. So this decides what type of amplitude you can measure, what kind of signal you can measure. So by varying this, how the seismic displacement response you can expect. So this give you the idea that how you can build your seismic instrument if you want to record a big earthquake, if you want to record a small earthquake. So which we will be discussing in the coming classes where what type of equipment, how it works. So this is how it works. Basically these are all the engineering subject mathematics, but this level you should know that how it works, that is more than enough. Okay, you no need to worry too much about all those derivations, solving of equation. Some of you maybe, as I said, that you may not study the engineering mathematics which comes on only on engineering degree, not on the other degree. So that is fine. So the seismogram, so as we explained that, so the mesh dance part, or if you have even a simple pendulum, so okay, with this one where you can mark a pen, so there is a drum which rotates to determine the location and strength, like the amplitude of the earthquake, which will help you. You can see here this is the normal condition. So when the earthquake vibrates, it start moving. So depends upon the star vibration, the nature, this will move very large and very less, and then it will again, when it comes to after the vibration comes, it comes to the rest. The sensitive instrument that can detect, amplify, record vibration. So generally whatever instrument records, they put some amplifier so that even a small motions can be also seen properly. Seismogram equipped with the sensor called seismometer that can detect a ground motion caused by a seismic waves from both near and distant earthquake. Some of the seismometers are capable of detecting ground motion as small as 100 millionth of the centimeter, 100 millionth of the centimeters. Okay, so which is close to the nanometer, micrometers kind of scale you can record. Okay. So this is the concept which again explains a modern seismic things in the electronic system. So where there is a coil which creates basically the gap between that. So this is the pendulum, so it's hold or mass, it is hold by the spring. Okay, so when there is a vibration, this mass will vibrate, there is a coil, the flux between this signal voltage difference will be created, that voltage difference will be amplified and then recorded as a volt versus time. Okay, that is how the modern seismometer works. So this mass and this will be deciding the what level of accuracy you should have. So basically as we have seen that so the earthquake need to be recorded on 3 direction. So there should be a 3 kind of voltage difference with respect to the mass arrangements in the equipment. Okay. So that you can get a 3 components of the recording and which will help you to get a waves. So we can see how these waves are get recorded through this video. You can see very carefully this video where it gives a how these waves are get recorded on 3 components.
Earthquakes produce different types of seismic waves that can be identified on seismograms. But did you know that each seismograph station produces 3 different seismograms for each earthquake? Why is that? Doesn't one tell you how big the earthquake was? Earth's movement is 3-dimensional, and one component only reflects one direction of movement. If a station had only one component, you would only know about movement in one direction. Different instruments on the seismograph measure 3 types of motion: up-down or vertical motion, north-south motion, and east-west motion. Let's take a close-up, exaggerated look at how a house would be affected by each direction of motion. When the house is shaken in the east-west direction, this shows up on the lower component. Nothing is recorded on the north-south or vertical components. When the house shifts north-south, this shows up on the second line. When the house is shaken in an up-down or vertical motion, only the top seismogram records the motion. During an actual earthquake, the house can move in all directions. Why is that? Earthquakes produce different types of waves, like body waves and surface waves, and these waves travel out from an earthquake in all directions. Body waves, like P and S waves, travel a curving path through the earth. As a result, they arrive at seismic stations from below. P waves are compressive waves that cause temporary microscopic deformation of the earth in the direction the wave is traveling. Thus, energy is primarily recorded on the vertical component of the seismogram, with less energy recorded horizontally. S waves move more slowly and are more destructive since they advance with a shearing or back and forth motion. Because S waves arrive later than P waves, they're usually seen on a seismogram as a second pulse. S waves cause deformation perpendicular to the direction of wave travel, which is primarily horizontal or back and forth motion, with less energy recorded on the vertical or up and down component. The slower surface waves, such as Love and Rayleigh waves, move in a more complex undulating pattern and thus show up on all 3 components. In conclusion, it is the combination of signals that gives seismologists information about the magnitude, distance, and type of earthquake that occurred.
So we could understand that so the earth produces a different direction of the wave. So to easily classify and characterize, at least you should be studying the 3 direct component of the waves. So which is like a vertical, 2 horizontal component. As you have seen that the P waves are basically a compressive and primary wave where you can see the dominant vertical component. But when you see the S wave direction, this may not be recorded. So any seismometer, so in the initial development they used a single sensor seismometer, but later they understand that the single sensor seismometer does not help. You need a 3 component seismometer. So that is why we need to have this one. So that means any seismometer should have some basic component to record a earthquake. So one is that a suspended mass hanging from the support attached in the ground. So such that where it can able to detect a vibration occurs on this 3 direction. So the inertia keeps them suspended mass stationary while ground moves below it. The movement is recorded as a rotating drum. So there is a drum which needs to be attached to the mass and suspended unit. Wherever that movement occurs, it will automatically record. So those days, olden days, as you are seeing nowadays, all of them was digital and mobile phone. So but in those days actually there is no electronic system was there. So the people used to record this in the drum which filed by the magnetic tape or paper, smoked paper, where they used to record. So to record waves, so this is basically a typical record. If you watch some of the scientific English movies, basically when the earthquakes occur, they show this kind of signal even today. But now all of them are digitalized, so we can also discuss about that in our class. So basically this reassembles this one. So this should have the mass, okay, with balancing inertial forces and a drum to record that vibration. So if you make that a simple component of that, you can build your own seismometer. So basically you can have a vertical wooden heavy weight like that. There is a horizontal frame which connected with the hinge here basically. Then you can have the mass which where it can be stationary when there is no shaking is occur, and then you can this can move when shaking is there. Then you can have a small portion with two drum with the paper. So then if you shake this, okay, by hit this will create a vibration. So this is how you can build your own simplest seismic instrument. Okay. So this even you can see homemade seismogram making in the YouTube. So there are a lot of explanations scientists are given. You can also, if you are interested to continue your career on this direction, you can see. For your information, India, we don't have indigenously developed seismometer which is capable of measuring the earthquake. Right now all the seismometers are India has been imported. Okay. So when you import and use, actually we will have lot of issues with the maintaining that, and then whenever there is a repair, all those things. These seismic signal basically
Seismic station will record 10 earthquakes to show how the data fit the travel time.
so will help to basically to get your waves arrival time.
The time that it takes for seismic waves to travel from the hyper.
So we will see the video one by one basically. So after building the seismoscope, basically you need to record your waves. We will see typically how these waves are recorded. Okay. So here you can see how the earthquake arrives and how the travel time has been created by the different seismometer in the world. So you can see like the distance from the earthquake and what type of wave you will get and the time shift which is happening. So this will help you basically to figure it out where that earthquake is origined. Okay. So which wave you are recorded. Okay. So that is what you will get from here. So here you can see basically the earth is given the distance and time in minute. So there are different places like 0, 10 degrees. So now the earthquake generated, you can see the understanding of the S and P wave where it recorded. You can see that 0.1, so the P wave arrived, S wave arrived. You can also see how the buildings are vibrating for that particular wave. Again you can see the, so S wave travels, P wave travels. Okay. So the P wave basically is slowly traveling than the S wave. So you can see that when you have the systematic placement of the seismic instrument, you can basically capture that velocity pattern very well. You can see here. So that is what it helps having the many seismometer installed. You can see here. Okay. So similarly the surface wave. So you can also see here when the waves are propagating, you can also notice here S wave and P wave shadow zone. If you are very clearly understood, so you can also see in the S and P wave shadow zone in this. So this is how you can get velocity at that particular location. You can see here the average velocity of the region which is called as a P and S wave region. So you can also see this video yourself with the audio where you can very clearly understand. So these things are useful to get a earthquake. Okay. So recordings as well as interpreting the earthquake data. Okay. So as we discussed that the amplitude and the wave speed changes with the medium. So having a same equipment throughout the region may not be able to detect all the earthquakes. So in that case basically the earthquake, which type of wave you want to detect and what type of instrument you need, we can get a overall idea. So this is basically the frequency of the wave, different waves which generally dealt in the universe, and the type of source which created. For example, earth tide means the earth rotation creates a vibration that basically in the range of, so this is the frequency range where you can see the this one. Okay, this is the earth tide. So then the earth free oscillating earthquake. So you can see this one, and surface wave earthquake. If you want to see that, that means if you have the instrument on this frequency range, you can only record a surface wave based earthquake. The surface wave P wave with earthquake magnitude above 6, you can expect this. So the P and S wave earthquake with magnitude above 2, you can expect here. The P and S wave earthquake magnitude less than 2, you can expect here. So if you want to measure all of them, your instrument should be on the combination of frequencies. Okay, that is what it has to do. So your selection of the particular frequency instruments are important to record the size of the earthquake and the type of waves, the size of the wave and type of wave. So based on this only you can get a data. Okay. So we will discuss about the more about the seismometer and how it works, and then the remaining things the next lecture also. So with this we will close this lecture. Thank you.